Welcome back. Now we start problems from section 6.1. Problem 1. Are the following statements true or false? If f and g are inverse functions, then the range of f is equal to the domain of g. Range of f is equal to the domain of g. That is a true statement. If f and h are reciprocal functions, then the domain of h is a subset of the domain of f. That is a true statement. Reciprocal means 1 over. H is 1 over f. That's what reciprocal means. So wherever f is 0, h is not defined. All right, and vice versa. So domain of h is a subset. Is f inverse x equals 1 over f? No, that is false. Inverse function is the reverse function. It is not a reciprocal function. For example, when fx is x to the power 3, f inverse is cube root of x. It is not 1 over x cube, it is cube root. So inverse is different from reciprocal. Given two functions f and g, f compose g compose x is g compose f compose f, but that's also false. For instance, suppose fx equals 2x plus 1, gx equals 3x. Then f compose g compose x means f of gx. Gx itself is 3x, right? We go inside out. Gx is 3x, f of 3x. F of anything is 2 times that plus 1. So 2 times 3x plus 1, that's 6x plus 1. Whereas g of fx is 2x plus 1. G of 2x plus 1 is 3 times 2x plus 1. So that's 6x plus 3. So notice 6x plus 1 is not same as 6x plus 3. So f of g of x is not in general g of f of x. Given two relations f and g, f of g of x equals g of f of x if and only if f and g are inverses. That's false. If fx is 2x and gx is 3x, then they are not inverses of each other, right? Whereas f of gx is 6x, g of fx is 6x. So they agree even though they are not inverses. So you see, when they are inverses, f compose g will be identity function. So is g compose f. When they are inverses, they will be equal, but there are other times also when these compositions can be equal. All right. Good. Next problem. What is the largest interval containing 0 on which fx is 1 to 1? Containing 0, okay? So fx is sin x. So sin x looks like this. So from 0, you want to go left and right. So you want an interval containing 0 on which f is 1 to 1. That is horizontal line test passes. So you see, from here to here, it's 1 to 1. Because once you draw horizontal, once you go beyond this, you no longer pass the horizontal line test. Once you go beyond this, you no longer pass the horizontal line test. So at negative pi over 2 until pi over 2, your function is 1 to 1. So negative pi over 2 until positive pi over 2. Good. Next. Without using calculator, cosine inverse of cosine of 5 pi by 4. Okay. 5 pi by 4. So I'm looking at cosine function, all right? Here is pi over 4, pi over 2, 3 pi over 4, pi, 5 pi over 4. So cosine of 5 pi over 4 is this value, is this y value. Notice I get the same y value at 3 pi over 4. Why am I choosing this? Because you see, from here to here, my function cosine is 1 to 1. Beyond it, it is not 1 to 1. Beyond this, I am not 1 to 1. So this is the piece that should get me the value. So cosine 5 pi by 4 gives me a particular height, which is also achieved at 3 pi by 4. So if I go inverse for cosine 5 pi by 4, I hit here cosine, so that's 3 pi by 4. 3 pi over 4. Next. Find the inverse of this particular function. Well, step 1 is to set y equals fx. So y is this fraction. Step 2 is to solve for x. So take this equation, solve for x. Cross multiply or clear the denominator. Y times 6 minus 4x is 1 plus 9x. Distribute multiplication by y. That's 1 plus 9x. Move the x's together, so negative 9x here. Move the y's, 6y to the other side. So you have x values, x expressions here, and the rest over here. Get x common factor, right? And divide by the factor. All right, so that you have solved for x. That's step 2. Step 3, interchange x and y. So where I see x, I write y. Where I see y, I write x. I get an expression. That is my inverse. Okay. So let's write down this inverse carefully. Because I have a complicated numerator, I will write parenthesis divided by parentheses. Okay. So now I can fill in the parentheses. 1 minus 6x, that's the numerator. Denominator is negative 9, negative 4x. That's correct. Okay, next problem. So fx is this polynomial. Its derivative is this polynomial, which has been simplified. Notice 1 plus x squared plus 2x squared. This is going to be positive. This is going to be non-negative. So overall, my derivative is positive. So f is monotone. That is, it's going to increase because derivative is positive. Since f has an inverse function, okay, because it's strictly increasing, it has an inverse function. Since fx approaches infinity as x approaches infinity, fx approaches negative infinity as x approaches negative infinity, it follows that the inverse function is defined for all numbers. Find the derivative of the inverse at 40. Okay, so we know we have an inverse function, we know it's continuous, we know its derivative. Well, we saw a theorem for the derivative. Derivative of the inverse at 40 is 1 over derivative of f at the inverse of 40. What is the inverse of 40? 3. How did I get it? I just guessed it, right? So look at this function. Okay, so plug in 3 for x. 1 plus 3, 4, plus 9, 13, plus 27, 40. So f inverse of 40 is 3. Okay, you need to find that x value, which gives me the answer 40. So that x value is 3. So I want derivative at 3 basically. Well, you have the derivative. Plug in 3. 1 plus 6, 9 plus 27, that is 34. So 1 over 34. So that's it. 1 over 34 is the derivative. Okay, so it's correct. So that completes section 6.1. My lecture notes here closely follow the text by James Stewart, which is our textbook for the course. Okay. Next section, I'll continue in my next videos. Until then, bye.